Good afternoon. Welcome everyone. Today we are building a little bit on what we discussed last week. If you made it, if you didn't, no problem. There's a recording of it available. Today we're discussing data visualization again, and we're discussing integrating real-time data for urban insights in Barcelona using a use case based in Barcelona. So we'll go to the next slide, please. Today, we'll have a very brief introduction to BDTI. We'll blast through this because we've got quite a lot to get through in the workshop. We will then give you our workshop on communicating complex datasets. We'll have time for a brief Q&A at the end, and then we'll wrap up explaining next steps. So as always, please do share your thoughts during the session. Feel free to use the chat and the dedicated Q&A widget for your questions. After the session, please do share your learnings with your network and remember to register for upcoming events. There are two more really interesting sessions for the rest of this cohort. So keep an eye out for them and make sure you register. The next slide, please. So yeah, I'll hand the floor over to my colleague Alex now, who will give you a very brief introduction to BDTI. Enjoy the session.
Hi everyone, thank you Kim for the introduction and welcome in today's session. For you that you have been also in the past sessions, unfortunately Maria Claudia, the person behind this initiation in general, was not able to join today, so I will try to present briefly, as Kim mentioned, the big data testing infrastructure, which is also the initiation behind these sessions that you are taking these the skills video sessions. BDTI is a data science playground specifically for people working in the public administration. It's a playground of open source tools that are offered in this platform, and people can join and develop and deploy these services, which are always on the cloud. Moving on the next slide, for you that are familiar with the data journey, as you can see here, there are few steps in the general data journey, and for each data journey we are offering some tools that the people joining the BDTI infrastructure will be able to launch and explore. As you can see, at least two of different tools are available for each step of this data journey. So there are plenty of tools for someone that will join the BDTI to explore and play and experiment with the data. Moving on, I would like to emphasize once again that it's a cloud environment which is offered for free for a 6-month period. This is offered in public administrators, no matter of the level of the administration. It could be, for instance, a small municipality or even a ministry. And of course, we are happy also and more than welcome to have collaboration with academia, like for instance, a student that might be interested in having a master thesis or a PhD with a collaboration with the public administration or even GovTech startups and spin-offs. And yeah, moving on here, and by using this QR code, by scanning this QR, you would be able to have a look on the pilots that took place in our platform, and some of them are currently running as well, but some of them are also in the past. I don't want to spend more time on this. So finally, I would like to explain a little bit the process behind of someone to submit in our platform. So once you have the data and in general the case that you would be interested in working on, you are able to submit a pilot. It's quite straightforward. You can find the request form in our website and submit your use case. Then we are going to assess the use case submitted, and if everything is clear and there is nothing to be discussed further. We are going to organize a meeting where we are going also to ensure that few requirements are clear, like not that no personal data are in the dataset that you would be interested in using. And once everything is ready, then we can move forward, and an environment will be set up for you and start playing around with big data test infrastructure. After that, there are a few steps like monthly meetings that we are communicating and check that everything is working fine and everything is improper. But this is to be discussed maybe on another session. So thank you, and I will move the floor to Berta and to show you the use case and enjoy the session. Thanks a lot.
Thank you, Alex. So welcome everyone, and thank you for joining this workshop. Today we will be exploring how open data, open tools, and real-time data integration can provide powerful insights for urban management and specifically for the public administration. So let's begin understanding what data visualization is and why it's so important. At its core, data visualization is the graphical representation of information, and by using elements like charts, graphs, and maps, we can better understand complex patterns in our data. It becomes specifically crucial when dealing with massive inputs or massive volumes of data generated from different sectors in the case of public administration, like traffic, air quality, public services, and more. In recent years, real-time data has become a game changer for decision makers. So it goes a step further and presents live data as it's being generated by allowing immediate insights into ongoing situations. Whether it's monitoring the traffic flow or air quality, having this up-to-date information at your fingertips enables more informed and timely decisions. So, for example, real-time data visualization can improve the response time to critical incidents. It can allow for proactive management of resources. It can support data-driven policymaking by highlighting the patterns as they are emerging. And in this workshop, we'll explore how to integrate real-time data into visualizations, turning raw information into those valuable insights. So we will automate and orchestrate the whole data process, and you will learn how to build a fully operational system that not only presents the data, but keeps it current and up to date. So now, what is orchestration? So orchestration refers to the automated coordination and management of complex data workflows. So in a typical data pipeline, you have collected, cleaned, transformed, stored, and then visualized the data. So instead of having to manually execute or perform each of these steps, automation ensures that the data flows seamlessly from the first step, from the source up until the visualization, so without the need of any constant manual intervention. For public administrations, making decisions based on outdated or incomplete data can lead to very ineffective policy or resource allocation. So with real-time data visualization and orchestration, urban planners and policymakers can base their decisions on current and accurate information. So this ability to make data-driven decisions in real time is what enables cities to respond way more effectively to evolving challenges. So now that we've covered the importance of data visualization and orchestration, let's dive to the practical side of this workshop. We're going to be trying to answer one key question that we'll set now in the beginning. So it's how can Barcelona improve public health and urban planning by analyzing real-time quality and traffic data. So what is open data? Open data refers to freely available datasets that anyone can use, modify, and share. So this concept is specifically relevant for public administrations, as open data fosters transparency, collaboration, and innovation. And each year, more and more governments around the world are increasingly releasing their data to the public, and this enables people like researchers, businesses, and even citizens to develop solutions to urban challenges. So in this workshop, we're going to be working with the Open Data Barcelona portal, which is, again, publicly available, and you will see how we access, analyze, and visualize this information to derive valuable insights. But there's other millions of open data sets available through platforms like data.europa.eu. And this European-wide portal offers data from various sectors and regions covering topics from environmental sustainability to transportation, public health, and way more. So yeah, just these data sets are free for reuse. In particular, for this workshop, we're going to be working with two main datasets. One on air quality dataset, which includes information about various pollutants collected from air quality stations around Barcelona. And this data is updated hourly, indicating whether the value that is shown is validated or not. And then the second dataset, which you can see here, is traffic data. This dataset provides insights into traffic conditions by sections of the city of Barcelona, and it's updated every 15 minutes, I believe. By combining these two datasets, we'll just demonstrate how public administrations can gain critical insights and just show patterns and and correlate basically the air quality levels with peak traffic times. We can make more informed decisions with those insights, and create better regulations or enhance the public transportation and optimize it. So this is what those two datasets look like. Just keep in mind that this is when working with real-time data presents challenges like data reliability, latency, and handling missing or incomplete information. This can complicate the analysis and decision-making process. Here, an overview of the tools from the BDTI platform that we're going to use. So we're going to start by setting up the environment, downloading the data. We're going to use Jupyter Lab for this, creating Jupyter notebooks with Python. Then we will store and process the data with PostgreSQL and Min.io to store the raw files and some output files that, as we will see. Then we will create a dashboard with visualizations on Apache Superset. And finally, we will orchestrate the whole process using Apache Airflow. So to ensure that we have enough time to cover everything thoroughly, we have pre-recorded the demo, but don't worry, we'll be here with you on the Q&A. So just make sure to, any question that you get during the recording or the demo part, please feel free to post it in the chat, and the team and I will be here to answer it. So without further ado, let's just jump straight into the tools and pay attention. So before we start working with the data, we need to set up the environment. Starting off from the BDTI website, I'm going to go into the portal, access it and log in. And then in the service catalog page, we're going to find all the tools available in this platform. So one of these that we're going to need is Airflow. So I'm going to launch and configure it. Starting off with the name, it's best practice to give it the name of the tool dash your initials, so that later everyone in the group that the instance is shared with will know who has created it and set it up. So it will be Airflow -cp. We'll make it shared for the ClearPix group and set a small configuration. If you attended the previous workshop, you will already know this, but the sharing status, we usually make it share so that all the people in the group have access to the same instance and we can share things. Then the configuration is it's an already predefined resources, so CPU, memory, etc. We can make it small, but if we were working on a larger project or we required more power, we could set a custom one or a smaller predefined one or a larger predefined one. Then this already sets up a username and password that we're going to be able to retrieve later from my data. And we just need to select the NFS, so it's the shared storage. We only have this one. And that's all. So we need to launch and continue. So the next tool we're going to need is Jupyter Lab for data science notebook. I'm going to launch and configure it. Make it shared for the ClearPix group and with a small configuration, and select the shared storage. Launch. Next is Min.io. And again, shared for ClearPix and small. We need to give the main user a username, so for now we'll use user1 and launch. Next we'll need pgadmin and PostgreSQL. pgadmin requires us to give it an email, so I'm going to use and launch. And PostgreSQL. Also shared for the same group and small. That's all. Now this step will take a while, so we just have to wait for the services to be created, and then we're going to be able to see them from the My Services tab. Once the deployments are ready, we can go ahead and explore the Min.io. Let's hit open. And we're going to be asked the credentials, which we can find in the BDTI platform on My Data Secrets. So let's find Min.io, the username, and copy the password. Log in. And the first thing we're going to need is to create some credentials to access later from a Python script. So we need to create a new access key. Clicking on access keys and then create access key. Create. And this is the only time we will have access to these keys. So make sure to copy it and store it somewhere safe. I will be storing it first in a notepad. Close, and now it's created. So we also need the Min.io URL, which is this part here. We need to use Min.io dash and the number. We're also going to store it here. And dash, we need to find out the name of the group. So go back to the BDTI platform and go to my account. And it will be this name here, so ClearPix. So our URL will be composed by this part here. So now we'll go back to the BDTI platform, and on My Services, we'll open Jupyter Lab. So click Open. And you might be asked some credentials, which again, you can retrieve from the My Data Secrets section. And note that here we can see some folders with some files in them. These are part of the shared storage we selected. So anything that we create and store here can be seen by the people we share the group with. So let's go ahead and create a folder for this project. We'll right click, select new folder, name it something like Barcelona, Greece, hit enter, and then double click to enter the folder. We can create a new Jupyter notebook, Python notebook. So you can click either here if you are in the main page, or right click new notebook. We'll select the Python 3, select, and you can rename it by right-clicking and hitting on rename. Name it retrieve data, rename, and now we're going to go ahead and write some Markdown. So Markdown is a simple language that allows you to include formatting instructions directly in the text, so bold, italics, cursive. And to do that, click on the first cell, and outside of the code area, you can either click here and Markdown, or click M on your keyboard, and this will now become a Markdown cell. We can write some text here with the text formatting already included here, and run it by clicking on the play button here. See, now the text is formatted, and we can go ahead and just add the code we want to use and some more Markdown. So now we have created some more Markdown explaining what this Jupyter Notebook does, and you will have this available in the GitLab repo of the workshop. But let's go ahead and take a look at what this first chunk of code does. The objective is to connect to the MinIO instance we created before, and then create a couple of buckets, and if they already exist, just move on. So let's break it down step by step. The first thing we're doing is importing some libraries for MinIO, for HTTP requests, OS to interact with the files, so to create new folders, etc. And then .env, which is the way we're going to store our credentials. Since it is best practice not to hard code the credentials onto the code, so we'll keep them separate in a .m file. Then what we're doing is loading the environment variables from this file that we have created with this function here, then storing the credentials from that file that we get as MinIO URL, access key, secret key. We're then using the MinIO function to initialize the MinIO client, which uses the URL that we set and got before, the access keys, etc. Then we're creating a list of the buckets that we want to create. We're interested in creating a couple of them, so one for the real-time data and one for the support data that we will need for this use case. And then we're actually creating the buckets. So we're looping through this list of 2 bucket names. And then for each one, we're connecting to MinIO. And then if the bucket does not exist, we're creating it. And if it exists, then we're just printing that it already exists. So let's just go ahead and create the .env file with the credentials. We'll go to this section here, right click and create a new file. And we'll name it .n. Now, as you see, once I enter, the file disappeared. This is because it's a hidden file, so we click on View and Show Hidden Files, and we can check that it has actually been created. If I double click to open it, it won't let me edit it. So what we need to do is to create a new terminal. So new terminal. This will open this part here. We're going to move into the Barcelona Breeze folder with doing cd. Run this. Now we're inside the folder. And we're going to edit this file with Nano, which is a terminal-based text editor. Just do nano.n. And this will open this text editor for us. We're going to enter the credentials here. So go ahead and enter your credentials. You can add it in this format. I've just added also some more credentials that we will need later to connect to PostgreSQL. And now to save this, we're going to do Ctrl+X, click yes, and enter to save it. Now this file is saved. We can go back to the code. And before we execute it, we need to make sure that we have these libraries. So for this is best practice if we want to import more than one library at once, to create a requirements file with all the libraries we need, and then just run it from the terminal and it will import them all for us. So right click here again, create a new file, and we're going to name it requirements.txt. Enter, we'll open it, and just list all the libraries that we need. For this use case, we're going to need this list here. Click Ctrl S to save it, and you can close. Now we'll go back to the terminal. And from here, run pip install. Again, this will make sure that all the requirements are met, and if there's one of the libraries that we don't have, it will install it for us. Great. Now we're ready to execute this chunk of code here. So you can click on the code and hit run. The buckets already exist, which is great. And if they didn't exist, it would have created for us. So the next step is actually downloading the files from the open portal, data portal from Barcelona, and then uploading them to Min.io. So what this chunk is going to do is import the necessary libraries again. Given that we have run this before, we don't need this. Then we're listing the URLs to download. We need some real-time datasets and then some support datasets. So real-time datasets are actually the pollution data and the traffic data. Then the support URLs are what each pollutant is, where the stations are located, etc. Then we're defining a function that will use get, so request.get, to make a HTTP call to each URL and save the response. Then once we do a call, we're getting a status code. So if we get 200, it means that it was successful. And if we get anything else, we just fail to download the file. And we're getting the status of the error, so why it failed. But if it was successful in this 200, we'll enter this part of the function here. First, we're extracting the name of the file name from the URL. So just getting the last part of the URL, which will be the name of the file. Here we are doing some workaround because in some of these URLs here, we don't exactly have the name of the CSV files. In these three cases here we do, but here we don't. This is because there's some redirections and we need to get the name in the redirection. Then we're saving the file content to a temporary local file and printing a success message if it worked. And then we're using the same Min.io connection we created before, selecting the bucket name and the file name to upload, and then we're saving it, storing it in the corresponding bucket. Then we're removing the temporary file we created, and that's it. So if we get an error, again, we will get an error message, and just calling the function for each URL and bucket here. Now I can go ahead and run this by clicking on here. We see that the files are downloaded successfully and then uploaded into each bucket. So now, yep, all of them worked. So this is ready. And we could go ahead and check from the Min.io console. In Object Browser, we have the two buckets here. And we already see from out here that there's some objects inside. So let's check the support data, for instance. And we see that it uploaded the files that we needed. So we can click here and download them if we want them locally or share them, etc. With the raw files stored as CSV in Min.io, we're now ready to create or work with a new Jupyter notebook in which we will explore the data, do some transformations to put it in the right format, and then finally store it in a PostgreSQL database. So what I'm going to do now is go back to Jupyter Lab and open the new notebook that we have ready. And let's break down step by step what this is doing. So again, as we saw before, This is first importing some libraries that we need, but they are in the requirements txt file. Then we're loading the .env file with the credentials, both the main.io credentials and the PostgreSQL credentials. Then we're doing the same as we did before, so initializing the main.io client, then reading the file qualitat ida from the bucket named Barcelona real-time, setting a path for the temporary files, and then getting the file from main.io. So with the client that we created before, we're using this to locate that bucket and file name and downloading it into the local file path, which is a temporary file path. Next, we're reading it as a pandas data frame and getting a message that it was read into a data frame successfully if we got to this point. Then we're removing the temporary file. And if it didn't work, we're getting a message and the reason why it failed. Now we're ready to execute this code. So you can either click run here or control enter and it will run. And we get the message that the file was downloaded successfully from the bucket and then that the CSV was read to the data frame. So now we have the data frame ready and we can explore it. We can see the first rows by putting the data frame name.head, control enter, and we see the first rows. We see that there's the code of the province, of the municipality, the station, and then we get a column per each hour and then another column indicating whether the value of that bulletin was validated or not. We can get the main statistics for each numerical column. So by doing describe, let's run this. And now what we could do here is to get rid of the columns that are not giving us any variation or information. So we see that there's some columns that have the standard deviation as 0 and they have constant values on all rows. So for every row in the data frame, the value is the same for these columns. It's not giving us any additional information and it's redundant. So we can get rid of such columns. We'll do that by putting the name of the data frame.drop and then list the columns that we want to get rid of. So control enter again here. And then we can check what this looks like now. Again, just the first few columns. Here it is. So now we don't have those redundant columns that didn't bring anything new to the data frame. So in this next chunk of code, we're using the .melt function to transform the dataset from a wide format where each hour has its own column into a long format where each observation has its own single row. So this change significantly improves the usability of the data, especially for analysis or time series analysis. In the original format, it was difficult to perform, again, time series analysis or filtering by the hour. And now we have reshaped it to a long format where we have one row per observation, and this will include the station, contaminant, value, validation status, and the timestamp. And yeah, let's just execute this and see what it looks like. Now we have the pollutant and the hours. Each hour will be in a separate row instead of how we had it before, structured like this. So we have found out by analyzing this, we go back to the description of the data, that the hours go from the hour 1 to the hour 24. And for time series analysis and to change and transform this into a timestamp, it usually goes from 0 to 23. So this is what this part of code is doing. We have such a long chunk of code because it's not as simple as just checking if it's 24 and if it is, turn it to 0 and increase the day by 1, because there's the case where the next day may be part of the different month, or the next we're in a year, in a leap year, and then we need to account for that, not just increase the day by 1. So we're handling that with this. You can take a look at the code from the GitLab repo. And then we're merging the day, month, year, and hour into one unique column, which will be named datetime, and dropping those unnecessary columns because now this information will be in the column datetime. So let's execute this. And here we can see what the new column looks like. Next, we can plot, for instance, the values for a given contaminant in a given station to see what that looks like. This is what this chunk of code is doing here. And we see this is the value of the pollutant number 22 for the station 43 over time. So for the last 3 days available. The next thing we're doing is actually uploading this transform data frame. So with 1 row per hour and per pollutant into a PostgreSQL database. So we're connecting to the database, again, as we saw before, getting the credentials from the .env file, creating the engine to PostgreSQL using the database username, database password, database host, etc. If you have any doubt about this, you can go back to the previous webinar on data visualization, where we also step-by-step connected to the PostgreSQL using Python. Then we're taking the final data frame and uploading it to SQL with this function from SQL Alchemy. We're naming it air quality transformed. So in PostgreSQL, the table will be named like this. And then if it exists, we will replace it to get the updated data. If we got to this point, we will print a message that it was successful. So let's execute this. Great. And the data frame was uploaded to PostgreSQL successfully. So let's move on. So now we're done with the real-time data cleaning and transforming and uploading it to PostgreSQL. But we also have the support CSVs that were in the support data bucket. So we will just directly upload those CSVs into PostgreSQL tables in the database. So the idea is the same one as before. We'll just run this. And we see that the 3 tables were successfully uploaded into the corresponding tables in PostgreSQL. So now what I'm going to do is to open pgadmin and check whether the tables were imported correctly into the PostgreSQL database. So we'll go back to the BDTI platform and look for pgadmin and open it. Next, if needed, you can add the new server if you don't have it connected already. You give it a name such as PostgreSQL CP connection, just put in here the address, which we can get from here, copy. We'll paste it. We don't need this last part here since it's already done there. Then the name of the database, the username, which is Postgres. We can find out what is the username from my data secrets. So let's look for PostgreSQL. The username is Postgres. And the password, we'll copy this one. Now, if we save, we should be able to see the connection. We have already connected to this, so it's down here. We can find the database, PostgreSQL CP. And inside database public schema, we should be able to see the tables. So under tables, we see the air quality transform, which is what the data frame we transformed with Python. So we can see the first 100 rows. And it looks fine. So we have the values, whether it was validated or not, and the timestamp, from which station and from which pollutant is this measure. Now we can do some transformations. So we can do some minor transformations using SQL queries directly in pgadmin. For instance, we can do a join with the pollutant description to the main table, air quality transform. And for that, we'll click on the left menu and select the query tool, and then just paste a script. So we'll go here, right click, query tool, write down the script, and if we execute it, we'll get the message that it worked successfully. And now under views, we should see the air quality with descriptions of the pollutants here. So again, just right click to view the first rows. Yep. And we get an explanation of what these codes are. We join this data. So if we go back to the query, we're joining it from the table that is named Qualidad Aire Contaminants, which is one of the support tables that we had uploaded from the CSV Minio to PostgreSQL database. Now we can start plotting the data and getting some visualizations. So we're going to start by creating a dashboard with Superset, which is one of the tools available in the BDTI platform. Then go to the BDTI platform and open the tool. Now we need to connect it to the PostgreSQL database. So on the top right corner, there's a plus sign. Click on it, then on data, connect database. We can select from multiple types of databases. We have a PostgreSQL one, so we'll select this one and input the port, the host, etc. So the name, the username, and we'll get the password from my data secrets. Display name is fine, so we'll connect. And now we need to create a dataset from this database. So we'll select the database, which is PostgreSQL, the schema, which is the public schema, and now the view we have created, which is the air quality transform data frame, but with descriptions. We see that the fields that are in this view are here. We'll create the dataset and create a chart. You can search the catalog from many different types of visualizations. And in this case, we can try to plot the last values for a given pollutant. So a time series line chart will be the easiest to interpret. We'll need to configure it, but first let's select the time series line chart, create new chart. We'll leave the time column as automatically selected, the date time column, but we'll change the time grain to hourly since we have hourly data. Next, we need to select a metric. We'll select from the simple ones. We want the value. And we can use any aggregation such as max, min, sum, since we are only expecting one value per pollutant code and per hour and per station. So let's hit save. We want to have it per station, so we're gonna use the dimension stations and filter it by the pollutant. There's two ways to use it here. So we can do that the code is equal to and the number, or we can take advantage that we now know the description of the pollutant, so the text field like and the value that we want. So we save and create the chart. And now we will see the value of such pollutant per station in the different time. So now we can customize the chart. We can add axis titles. We can change the colors. We can show the values, tag the series, add a marker. We can allow for data zoom. So if we want to only see one part of the data of the series, we can do that. And that's it for now. So we'll update the chart to make sure everything is updated and make sure to add the name of the chart. Percentage per station. Great. So now we can save it by clicking here. Let's save and click on the plus button again and add a new dashboard. We can add a new chart by clicking it and dragging it onto the area. We can change the size of it, maybe make it longer. We can name this dashboard something like air quality in Barcelona. And now this is total creative freedom. So you can go ahead and add other things. You can add filters, you can add more graphs. Now this is only some basic analysis, so descriptive. You can also create your own predictions, show them in this dashboard. Right, so now we can add some interactivity by allowing to filter by station in case we want to see a subset or just one. So we'll click on the left and click on add edit filters. We want to add it by value. We'll call it station or stations. Filter by the station code. And allow selection of multiple values, so we just save. And now we see here, we can just, if you want to see only for stations 43 and 44, for example, click on apply, and the graphs will automatically update. Note that we have also added some text. You can do that by clicking edit dashboard and layout elements. You have many options here. So once you're happy and have arranged this and it's however you liked it, you just go ahead and play and customize it however you like it. So once you're ready, just click save. In this case, no changes, so discard. And the dashboard will be ready. You can export it here, so save as, download as image, share, etc. Now we'll go back to Python. So navigate to the Jupyter page and create a notebook. We'll call it creating map IPython notebook, and we'll load from min.io the datasets needed to see the real-time data in a map. And first we'll start by reading the CSV files with the strict sections which have traffic sensors. So go on here and we'll create the script. So here we have the script ready. It does basically the same as we have been doing before in the beginning. So loading some of the libraries, getting the credentials to enter min.io, creating the client, then reading the transit or station or radar sensors CSV, which is in the support data bucket. We're reading this file. We can execute this. It works. We can see the head of this data. So it's the code of the section, the description, and the coordinates. So markdown. So now we load this data on the information on how bad or how good is the traffic right now in these sections. This is the trams underscore trams.dat file. We'll see that this has, so we'll execute this, and we'll see that this has a strange format. So as stated here, you will have this file in the GitLab again. The structure of this file is a bit different, so it's separated by hashtags, each column. And first we have the section identifier. So this 1, 2, 3, 4, 5 is the section identifier. Then the date in the format year, month, date, and the time. So this is the timestamp. Then the current state of the traffic, and then the predicted or expected state of the traffic in 15 minutes. So we even get some forecasts. So now we want to transform the data to look like an actual table. So we'll select the name of the columns, we'll give them that. So first we'll split it by the hashtag and then give them the names. And then we can transform to date time. We format properly the date type column. And once that is done, this is what the data will look like. So it's just the same thing, but with column names and with separated by the hashtag. So in this next chunk, what we are doing is merging the two data frames that we have just loaded. So one with the description of each section and the name and just the location, and the other one with the information of the current state of the traffic and the forecasted state of the traffic. So this is what is done here, just dropping the missing values and creating the left join. So let's execute this. Here we have all the columns. We have dropped the tram column because it's just duplicate of the section ID. It's the same one. And next, what we can do is to create a map that shows exactly what is the status of the traffic in the map. So it's interactive. So if we hover over a section and we click on it, we will get the values for that. We will not go line by line in this case. If you're curious on how this works, please go ahead into our GitLab repo and explore the code by yourself. But basically, the result of this chunk here, it is loading, so we have run it. Great. So the result is this map, and we can zoom into the map of the city of Barcelona. We can click, for instance, in this section here, and we'll get the name of the section, the current state, so it's number 2, so the traffic is fluid, and it's forecasted to be fluid also in the next 15 minutes, and the time of the measure that was taken. And then what we have also done is to save this as an HTML. So each time we execute this chunk here, this will save this HTML that we create, so the result of this, into our min.io bucket. So we are saving it in the Barcelona real-time bucket and naming it Barcelona Air Quality Stations with sections HTML. So if I go ahead and execute this, it has been uploaded to the real-time bucket successfully. So if we go back here, object browser, Barcelona real-time. So we'll click on the object and hit download. Now we have downloaded this, we can click on it. And we have the file, so the HTML, again with the same interactivity, so we can click on it. Here there's no data, but in this section, for instance, it's pretty high traffic right now and it's expected to be also in the future. So yeah, we can go ahead and play and add new layers. We can add the air quality layers, so to try to locate whether each point where the traffic is close. So maybe in this section the air quality is not so good. Maybe up here it's good. We can try to see. So just play with this data. You can go back to Jupyter here, to the Jupyter notebook here, and add new layers in this code if you want to play around. Again, in the GitLab repo, you will have everything. So yeah, let's just jump to the result, not to bore you with explanations on how this is done and what exactly each line means, since for your use case, this may change if you want to do something different. So now we have added some data on the air quality, reading the transform data that we have on the PostgreSQL database. So we're connecting to it in this chunk of code here and selecting the view that we created before, saving it as a data frame, viewing the first few rows, and then downloading the support data to know the location of the stations from min.io, and just seeing the first rows and joining both to know for each value and air quality recording at each point of time where the location of the station is. So just doing a left join basically. Then getting the latest per station and pollutant validated value. So 1 row per each of those. And then here, basically, we have modified the map to include this data in a beautiful manner, and then adding the pop-up so that now when we select, so we can, again, still move the map, and we can click on a station. So these points here are the different stations, and see the values of the latest values of each pollutant or contaminant. And then with some field knowledge, we could analyze whether the areas with highest traffic or traffic density have more pollution and would require some sort of action. So that's it for creating the map. And now let's move on to the next part. So now that we have gone through the process of setting up our environment, retrieving and transforming data, and creating visualizations, the next step is to ensure that all of these tasks are automated, efficient, and maintainable. So this is where Apache Airflow comes into play. Apache Airflow is an open source platform that allows us to orchestrate, monitor, and manage complex workflows, but by defining them as DAGs. So instead of manually running the tasks like the data extraction, transformation, and visualization scripts that we have created, Airflow automates them on a set schedule in response to specific triggers. So from the BDTI My Services tab, we're going to find Airflow and open it. And the first thing we need to do is to connect Airflow to our PostgreSQL database for some tasks that we're gonna run. So go to Admin Connections. And here you can click on the plus icon to create a new connection. It's a Postgres one, so Postgres. And just like what we have been doing before, put the host, the port, the username and password, the schema, which is the public schema, etc. Now we're going to go back because we already have the connection here. Give it a connection ID. For instance, we have used my Postgres connection. And the next step will be to create the DAG. So for that, go back to the Jupyter Lab, and we have created a folder named DAGs. Inside of this folder, we have a Python script for the DAG. And here it is. So once the file is open, we start by defining the DAG. So the first thing that we need is to set up the default arguments like the start date, retry policy. So how often we're going to retry, and the owner of the DAG. And this is important for handling any potential errors or retries during execution. So next we define the actual DAG. We're naming it Air Quality Pipeline and setting it to run on an hourly schedule or a daily schedule, as the air quality data is updated every hour and traffic data every 5 minutes. For simplicity, now we'll just run this pipeline every hour to keep everything up to date. And with the basic setup in place, we'll move on to creating the individual tasks for our pipeline. So let's just set this to hourly, so that it runs every hour, and then setting for each task. So the first task will execute the retrieve data Python script. Next, we will run the transforming data Python script, which will then upload the resulting data frame, if you remember, and the support data frames into a PostgreSQL database. Then we're doing some transformations directly using the My Postgres connection that we have created before. So we're doing them in SQL with a Postgres operator. And then finally, we're running the create map Python script that we have just seen right now for creating the visualization and defining the task dependencies. So we want this to execute as a pipeline, so one script running before the other. So this is the order that it should run into. After a while, so once we have added this to the DAG folder and wait for a bit, if we refresh, we will get the air quality pipeline here that we have just created. And it will run, so hourly in this case. And then we can trigger the DAG manually here or wait until the hourly trigger is set. I'll select the last run. And from the graph, we can see the different tasks that we have added onto this DAG. So we have the execute retrieving data, execute transforming data, create air quality view, and execute the create map. So all of these every hour will be executed. And if successful, it will be noted here, so tag it as a success. And if not, we will get the error or the reason for the error. Finally, we can also set up a superset schedule for the dashboard we created earlier in the workshop to be refreshed hourly. So we will keep up with the changes. And here's how I'll do that. So we have to go back to the superset instance here. And then on the three dots on the top right corner, we'll set auto refresh interval, and we can set the refresh frequency. We may be interested in doing it in 1 hour, or if we change the DAG to execute every 5 minutes, since the traffic data is coming in every 5 minutes, then we can set that. For now, we'll just put an hour and we can save it. Now this dashboard will automatically refresh every hour. And this way we don't need any manual refreshes, and we will ensure that the data always reflects the most recent air quality and traffic data. Okay, so let's wrap up quickly what we have covered in this workshop. We started by setting up our environment in the BDTI platform, deploying Jupyter Lab for running the Python notebooks and Min.io for the data storage. From there, we retrieved the air quality and traffic data from the Open Data Portal, and we stored it securely in Min.io. We then created a pipeline to transform the data, ensuring it was structured and clean for the analysis. We transformed it and loaded it in a PostgreSQL database. And then we set up a foundation for later creating a visualization in Apache Superset, so creating an interactive dashboard. And we also created an interactive HTML map using Python, where we can visualize traffic and air quality data on the city map. And we added some interactivity for better data exploration and stored this HTML file and the map to Min.io. And then we orchestrated all of these processes by creating a fully automated Airflow pipeline and set a schedule for the Superset dashboard. With that, we have successfully walked through the entire end-to-end pipeline. And to conclude the workshop, we will revisit the key question that we posed at the beginning of the workshop. So how can Barcelona improve public health and urban planning by analyzing real-time air quality and traffic data? So by analyzing the data we have been using, we can identify correlations between air traffic congestion, pollution levels, and maybe we can add another layer for the green spaces across the city. So these insights allow us to propose strategies that improve both urban planning and public health outcomes, but keeping in mind that statistical correlations show how two variables move together, but correlation doesn't mean one causes the other. So causation by contrast is when one variable directly influences the other, creating clear cause and effect relationship. So let's say you analyze the data from Barcelona and find that traffic congestion increases, air pollution levels also increase. So this could suggest a positive correlation between traffic and pollution. However, this does not mean that traffic alone causes pollution. It's simply that they occur together. So other factors like industrial emissions or weather patterns could also be contributing to the pollution levels. So now after the analysis, we can just propose some recommendations for the public administration, maybe for the Barcelona municipality. So if we have detected that some green spaces, by adding a new green spaces layer, have high pollution levels and high traffic, we can, for example, expand the green spaces, so increase the number of public green spaces, especially in the zones identified as having limited greenery and significant traffic congestion. We can also enhance the pollution migration near sensitive sites, so prioritize the planting of trees and creation of green barriers around sensitive areas, such as schools, hospitals, and residential zones. We can also integrate green corridors, so develop a corridor that connects existing public parks and green spaces, especially in high traffic zones, to provide a continuous natural buffer. And this can make the city more walkable and improve residents' access to nature. So having worked through this use case, keep in mind that this is just one example of how open data can be used to solve real-world challenges and real-time challenges. So similar approaches can be applied to other data sets, whether it's energy consumption, waste management, or public health statistics. The key takeaway is that by leveraging open data and real-time data visualization, public administrations can build more responsive cities. So now you will leave today's workshop equipped with the tools to do such analysis and having an understanding of how these technologies can drive better decision making and improve the quality of urban life. So we will leave, as I mentioned before, the code and just all the resources and materials in the Skill Studio GitLab repository, which you can retrieve from this link here. I believe it will be sent to you later also on the email. And that's it. So now if you have any questions to ask us, feel free to post them in the chat and we will be happy to answer them.
Thank you, Berta. That was a really, really interesting and informative session. If there are any questions, please do feel free to pop them in the chat now, and we'll post to Berta. One I did see come in privately asked, why are we using JupyterLab instead of Spark for this use case?
Yeah, so Spark is optimized for the large-scale data processing, so for distributed computing and all of that. In this use case, the amount of that data that we have is much more manageable. JupyterLab is great, so it's very well suited for this kind of data sets, and it provides this interactivity, so we can execute it chunk by chunk, the code, if we create a Jupyter notebook. So it was key for this workshop. That's why we chose this approach instead of Spark. Yeah.
Great, thank you. Another question that came in privately actually was more to do with the BDTI infrastructure, asking how it's hosted and set up. Demeter, we have posted the documentation link for you there, so hopefully that works and you can find everything you need to find there. One more question then I think came in privately. What is the role of the .env file in this project, and is it really necessary?
Yeah, so maybe it seems like it's overcomplicating the code, but it serves as a secure storage for the credentials that Jupyter Notebook then will use to connect to the services like MinIO, PostgreSQL. And this helps us to keep the code clean and to separate the configuration from the actual code. And it's more maintainable. So if we change the credentials, we just need to edit that .env file. There's other ways to do this. You can do your own research, and yeah, there's other alternatives, but the best practice in general is to keep in mind that we need to avoid hard coding the credentials into our main code, right? So that's why we use this .env file.
That makes sense. Great. I don't see any more questions. We have 4 more minutes, so maybe we'll wrap up. If you wouldn't mind, Berta, just flicking to the next slide, please. I hope you all enjoyed that really in-depth session. If you did enjoy it, we've got 2 more for this cohort. In early November, we're going to be talking about harnessing climate data using predictive analysis, and on the 20th we'll be diving a bit more into real-time forecasting, predictive modeling. Really interesting stuff coming. You can find more information using this QR code and registering for those events there. Just to wrap up then, are you eligible? If you're European public administration at any level, you're eligible to apply. If you're in academia or in the private sector and want to collaborate with the public administration, you're eligible. If you're not sure, please do email us and we can discuss and figure out how you can come up with a nice use case. That's it. Yes, learn more about BDTI here with these fancy QR codes. And if you have any questions or want to find out any more about BDTI, please do stay in touch and stay up to date. Thank you so much for attending today, and we hope to see you in the future sessions. Have a great day, everyone. Thanks, Berta. Thanks, Alex. Thanks, everyone.